In this video, we examine 4 steps for an effective low-error algorithm for regression analysis when using a laptop. We know that most machine learning approaches need tuning and various trade-offs for best results. For this reason, it is important to have a high-quality starting point, which is like a framework, and one that includes an effective machine learning algorithm. These 4 steps I'm going to talk about should help set up that starting point. We will use Python as our programming model, but these steps should be general enough when used with any language or tool that's appropriate for machine learning. We will indicate exactly in our Python code what those 4 steps are and how to go about them. In the end, I will show how by using those 4 steps, we will build a high-quality starting point for regression analysis using your laptop. For following along with this video, you will need a decent laptop running at least Windows 10, Jupyter Notebook at Anaconda 3 level installed on your laptop, a working IPy kernel in your Jupyter Notebook with required Python libraries. Okay, let's dive right in. In regression analysis, we set out to fit data from a given problem to a regression model and estimate the parameters of that model. We don't always have the knowledge of the physics of the problem to be able to dictate the type of regression model to start with. Many real-world processes need us to fit their data to a polynomial. But then, how do we choose the degree of polynomial to use? So the first step is to identify a polynomial function of an appropriate degree that adequately represents a physical process in our regression problem. Our goal is to estimate the minimum degree that keeps the polynomial model simple yet fits the data well. Let me generate my dataset with a known polynomial function. That is step 2. By the way, I will use a single independent x variable in my dataset for now to keep things simple. I won't reveal the known polynomial function I used to generate the data until towards the end of this video. Instead, I will estimate the coefficients and intercept of my regression polynomial function by fitting it to the data that I generated. This is step 3. In step 4, which is the final step, I will compare the estimated intercept and coefficients from my polynomial regression to those of the function that I originally used to generate my data. Remember, I did use a polynomial function to generate data in the first place. So, on to step 1. To begin with, I have imported the necessary Python libraries in my notebook. For example, scikit-learn here or scikit-learn is a very useful machine learning library for Python. I use pandas for data loading, matplotlib for plotting data, and numpy for data structures and some mathematical functions. I am going to start by using polynomial features with degree equal to 2. I will use polynomial features to transform x values from my dataset to those appropriate for a polynomial function of degree 2. The method fit_transform here does the transform from x. Let us examine how the x values are transformed. x_poly_regression holds the transformed values. Notice that the first feature is x to the power 1 and the second one is x to the power 2 in the transformed set. Heading to step 2, here is a plot of data I generated from a polynomial function, a function that I know beforehand. Let me know in the comments box what order of polynomial this function might be, just by the look of the data plotted. With the data being generated, let's head to step 3. In this step, I will set up a linear regression model from scikit-learn library. Linear regression will fit my data such that the residual sum of squares between the observed y values in the dataset and the y values predicted by the model is minimized. Note that I have left the fit_intercept parameter of linear regression to the default value true, which means the intercept for this model will be calculated. One thing to note, even though my dataset is for a polynomial function, which means the xy values in the dataset are not linear, we still use the linear regression model from scikit-learn library to fit our data. With that done, we now head to step 4, which is the final step. Next, the fit method of linear regression is called to fit our model to the quadratic dataset we generated. Note, the quadratic dataset is the transformed x values x_poly_regression. The y parameter in the fit method is the set of y values in our dataset called targets. We now inspect the intercept and array of coefficients which were estimated from fitting our dataset. Now is the time for the reveal. I am going to compare the estimated coefficients and the intercept with those of the known function I used originally to generate my dataset. We can see that both the intercept and coefficients are close estimates of their original counterparts. The degree of the polynomial is 2. In other words, we used a quadratic polynomial. This is one indicator that our basic framework for polynomial regression is now set up. That is, A, we have a way to transform our regular x values to those that are appropriate for a polynomial function with a desired degree, and B, we are able to fit a regression model to this transformed data and estimate the intercept and coefficients of that model. In machine learning terminology, we have now trained a quadratic polynomial model, and the dataset we used is called the training data set. Let us visualize how well our regression model, with its estimated intercept and coefficients, fits the training data. The blue dotted line here is our regression polynomial function that we fit over our training data. The red dots in the plot represent the training data. At this point, our basic framework for regression polynomial is set up. The blue line here seems to fit our theoretical quadratic data points well. Now, imagine that there is a physical process somewhere that is approximately represented by our quadratic model. And I say approximate because real-world problems don't always fit theoretical polynomial models like quadratic or cubic perfectly. So, if we try to approximate that real-world process with our theoretical quadratic dataset, we are not sure yet that the quadratic polynomial function we estimated, and by that I mean the polynomial function with its estimated intercept and coefficients, is able to correctly predict all the y values in that physical process with independent x values from the process space. If I can simplify this a bit, we have a finite number of data points in our dataset. See here, n is set to 300. In machine learning terminology, we have 300 training examples or instances or samples. Our quadratic polynomial function seems to closely fit our 300 examples, but we are not sure if it will fit the entire set of x and y values which are in the space of that physical process. In other words, we're not sure how well our estimated quadratic model is generalizing to that very real-world problem it is trying to approximate, which is really our end goal. We call this a problem of overfitting if our model fits our training data from a process space well, but poorly predicts y values from other independent x values in that process space. We call this a problem of underfitting if our problem both fits poorly our training data and predicts poorly y values from independent x values in the process space. There are methods to track the generalization performance of our regression function. I am going to pick up a visual method. Up until this point, we used all xy values from our dataset for training our regression model. Instead of using the whole set for training, we are now going to split our xy values from our dataset into what we call test and training sets. We will allocate 30% of the data as our test set while retaining the remaining 70% in our training set. We use train_test_split from scikit-learn.model to implement this. Feel free to try different settings such as 25% test set and 75% training set. We can set the desired proportion using the test_size parameter here. We use mean_squared_error from scikit-learn to calculate mean squared errors. Next, we allocate two arrays. The first one to store mean squared errors from training passes. The second one will store mean squared errors from testing with the test dataset. As we will see in a second, we set up a loop where we train the model starting with one example in the training set in the first pass and adding an example with each next pass until we train all examples in the training set in the final pass. We have set 70% of our data as training set. Remember, we set total example size. N is equal to 300. That means our training data set has 210 examples. So in the loop we have set here, we will make 210 passes. In the first pass, L is equal to 1, that is, our model will be fit to one example in the training set. In the second pass, L is equal to 2, That is, our model will be fit to 2 examples in the training set. Likewise, in the final pass, L is equal to 210, our model will be fit to all 210 examples in the training set. With each pass, the mean squared error between y values in the dataset and y values predicted by the model is supposed to be progressing towards an optimum value, since we are adding examples in the training with each pass. Note that I said optimum value, because the mean squared errors will start out high with fewer examples in the initial passes, but as the model learns from more examples, the mean square error will reduce to an optimum value. Beyond that optimum value, adding more examples in the training may not reduce the mean square error further. We track the mean square error of predictions in each training pass and store it in y_train_predict. Whatever level of learning the model is at every pass. We test the model by predicting the y values in the test set with all x values in the test set. We expect that if the model is training towards an optimum level, the y_test_predict values will also approach an optimum level. So, if the training is progressing to an optimum level, the plot of y_train_predict and y_test_predict should ultimately show a tendency to converge by the time we make all 210 passes of the loop. We now run polynomial features and linear regression with 210 training examples as a pipeline. And call the plot_learning_curve function with the polynomial_regression object as one of its arguments. X and Y are its other arguments. The graph here visualizes what we call learning curves, which are nothing but a plot of mean square errors in the y_test_train and y_test_predict for each training example. In summary, we now have a basic framework for polynomial regression. In order to make the model work for specific physical processes, it requires further tuning and trade-offs. For example, in choosing an appropriate degree of the polynomial and what we call regularizing the model. These topics are not covered in this video. The final model will be a trade-off between bias and variance. Bias is a kind of generalization error in which the degree of the polynomial is set at a lower value than what is really required by the physical process it represents. This can cause underfitting. On the other hand, a polynomial with too high a degree can cause overfitting, which is a high variance problem. That's why we call the ultimate model to be a trade-off between bias and variance. I hope this video was helpful in your learning journey. Please share your comments, which can help us make more such content in future.